Let us study the refraction of light at a spherical surface in detail. Let C be the center of curvature of the spherical surface, AB be the principal axis, and P be the point of intersection of the spherical surface and the principal axis. If a ray of light is incident on the spherical surface, it refracts to the second medium. In order to apply the laws of refraction, we need to draw a normal to the spherical surface at the point of incidence. Normal to the spherical surface at any point can be drawn by joining the point to the center of curvature C. For example, if P, M, and N are three different points on the spherical surface, then PC, MC, and NC are the three normals at the 3 points mentioned. Let us assume that the first medium is optically rarer compared to the second medium, and place a point object O on the principal axis in the rarer medium. Now consider the light ray OP. Since it is incident normally on the spherical surface, the ray OP propagates to the denser medium without any deviation. Whereas, rays like OM and ON, after refraction, bend towards the normal because they pass from a rarer to a denser medium. All the refracted rays converge to a point on the principal axis and form a point image I. Here, PO is the object distance U and PI is the image distance V. And if the radius of curvature is R, then PC is equal to R. Before we derive a relationship between the object distance and image distance, you need to know about the Cartesian sign convention we follow in case of refraction at a spherical surface. This is similar to the one you learned in the case of mirrors. The conventions are 1. All measurements are made from the point of intersection of the spherical surface and the principal axis. 2. Measurements are taken as positive if they are in the direction of the incident light, otherwise they are taken as negative. 3. Lengths measured upwards are positive. They are negative if measured downwards. Let us now derive an object, image relationship for a spherical surface. Let the refractive index of the rarer medium be N1 and the refractive index of the denser medium be N2. If the aperture of the spherical interface is small when compared to the object distance U and the image distance V, then the following approximations can be made. 1. Arc PM can be taken as a line perpendicular to the principal axis. 2. The angle of incidence and the angle of refraction are very small, and hence tan and sine functions of these angles are approximately equal to the respective angles. Let the angle MOP be theta 1, angle MCP be theta 2, and angle MIP be theta 3. Then, tan theta 1 is equal to PM by PO, tan theta 2 is equal to PM by PC, and tan theta 3 is equal to PM by PI. Since the angles are small, tan theta 1, tan theta 2, and tan theta 3 are approximately equal to theta 1, theta 2, and theta 3 respectively. Then we can write that theta 1 is equal to PM by PO, theta 2 is equal to PM by PC, and theta 3 is equal to PM by PI. For the triangle MOC, I is the exterior angle and is equal to the sum of the two interior angles theta 1 and theta 2. This can be written as I is equal to PM by PO plus PM by PC. Let this be equation 1. Similarly, for the triangle MIC, theta 2 is the exterior angle and is equal to the sum of R and theta 3, or R is equal to theta 2 minus theta 3. This can also be written as R is equal to PM by PC minus PM by PI. Let this be equation 2. But according to Snell's law, sin I by sin R is equal to N21, and we know that N21 is equal to N2 by N1. Therefore, N1 sin I is equal to N2 sin R. For small angles, this can also be written as N1I is equal to N2R. On substituting the values of I and R from equations 1 and 2, and after further simplification, we get N1 by PO plus N2 by PI is equal to N2 minus N1 by PC. Let this be equation 3. But, on applying the Cartesian sign convention, PO is equal to minus U, PC is equal to R, and PI is equal to V. On substituting these values in equation 3, we get N2 by V minus N1 by U is equal to N2 minus N1 by R. Let this be equation 4. This equation gives a relationship between object distance and image distance for refraction at a spherical surface, and is valid for all types of spherical surfaces. We know that when a light ray passes from denser to rarer medium, it partially refracts to the rarer medium and bends away from the normal, and partially reflects back into the denser medium. This reflection is known as the internal reflection. In case of refraction from denser to rarer medium, the angle of refraction R is greater than the angle of incidence I. If another light ray with higher angle of incidence is considered, its angle of refraction will also be correspondingly higher. If the angle of incidence of the light ray is gradually increased, then, for a specific angle of incidence, when the angle of refraction in the rarer medium becomes 90 degrees, the refracted light grazes along the interface. This angle of incidence in the denser medium is called the critical angle C for the pair of media under consideration. That means, if I is equal to C, then R is equal to 90 degrees. Let N21 be the refractive index of the rarer medium with respect to the denser medium. Let N12 be the refractive index of the denser medium with respect to the rarer medium. We know that N12 is equal to 1 by N21. As per Snell's law, N21 is equal to sin I by sin R, which is equal to sin C by sin 90. Therefore, n21 is equal to sin c. Or n12 is equal to 1 by sin c. This means the refractive index of the denser medium with respect to rarer medium n12 is equal to 1 by sin c. If the angle of incidence is made larger than the critical angle, the incident light cannot refract to the rarer medium and is completely reflected back into the denser medium. This is known as total internal reflection. Since there is no transmission of light to rarer medium, light gets completely reflected back to the denser medium. That is, it gets totally internally reflected. Hence, for light to have total internal reflection, it must satisfy the following conditions. 1. It must propagate from denser medium to rarer medium, and 2. The angle of incidence must be greater than the critical angle for the pair of media.